Hey guys, welcome to the 10th video of Module 7. And here we are going to code the artificial neural network from scratch. Everything that we have understood so far in this module, we are going to implement it and code it completely from scratch. Make sure to download the code along file and code with me, where we are going to complete all the equations for the cost function, forward propagation, backward propagation, then train the model and finally test it and see that how much comfortable we are with the artificial neural network. So let's get started. Alright guys, so I'm ready with my code along file. I hope you are ready with your code along file as well. If not, I recommend you to just open this code along file and start coding along with me. And yes, what you are seeing over here is not the true architecture that we are going to use, because in our case, we are having two inputs, four hidden neurons, and then one output neuron. But yeah, that's the design of the architecture that we'll be using. And then this is the equation for the cost, the forward propagation equations, and the backward propagation equations. Along with that, we are having this gradient descent. And lastly, this data set that we are first going to build. And then on top of that, we're building all the type of different functions and finally train it. And then the first step is to start by importing these libraries. So I'm having NumPy for this kind of manipulation of the data. And then the matplotlib pyplot module from the matplotlib in order to display the outputs. So what I've done is I've already prepared the dataset over here for us. I've used NumPy array with 4 different rows and 2 columns, and we are seeing that there are 2 rows with the same values and then the 2 rows with the different values. So all of these things is ready for us for the input part. For the output part, we are having 0, 1, 1, 0, or I should say, to be honest, with respect to this data, the way we have built, in both of these things, when the values are equal, the output will be 0. So that's what you are seeing over here. And similarly, when the inputs are different, the output will be 1. So yes guys, our data set has been ready already. So I'll just run this. Along with that, I'll also print the data just to see that everything is working fine. So yeah, 4 rows, 2 columns for the X, and for the Y, I am having 4 rows and 1 column. After this, I'm going to design my architecture in terms of how many neurons in my input, how many neurons in my hidden, how many neurons in my output. So now I can run this code cell. I'm setting the SID value of 74 over here so that I will be using it to prepare my WXH and WHY. So in order to prepare the WXH, this is the connections that I'll be having in between num input and the num hidden. So I'll copy that, paste it over here. That is basically 2 cross 4. And then if I run this code, you will see that the output shape must be 2 cross 4 as well. And then if you want to look into the matrix, the random values that we have filled over here, that's how it's really going to look like. We don't really care over here that how we are designing this kind of 2 cross 4 matrix. You can have any kind of random values the way you want it. And therefore, this is something that is going to be the starting point for the XH weights of this whole architecture. After this, I'm going to repeat this step for the WHY, and it's going to be 4 cross 1 as you know already. And that's how the weights are going to look like, the initial weights of the WHY parameters. Now after this, we are going to start defining all the functions that's going to help us create our neural network, starting with sigmoid activation. So over here, I'll just scroll over here and write my activation output as 1 divided by 1 plus np.exp of minus z. So 1 divided by 1 plus e to the power of negative z is the sigmoid that you must be aware about by now. So yeah, that's what I've created over here. After this, about the sigmoid derivative, I'm going to written what? It is sigmoid times 1 minus sigmoid. If I show it to you over here. So we know that the center part, the derivative of the y cap with respect to your z2 is going to be your sigmoid derivative. So it's going to be sigmoid of z2 times 1 minus sigmoid of z2. So sigmoid times 1 minus sigmoid, that's it. So if I come back, sigmoid of whatever is the z, multiply that with 1 minus sigmoid with that same z. So that's your sigmoid derivative ready. Now after this, you need to know that at the rate stands for the matrix multiplication, and then this asterisk stands for the element wise multiplication. So how can we have our forward propagation equations? Over here, I'll be first of all requiring z1. After z1, I'll have my a1. After a1, I'll have z2. And after z2, I'll have my final output, that is your a2, or the prediction, whatever you'd like to call it. But yes, these are the kind of things that I'll be having, and let's compute it one by one. So for the Z1, if you remember, it's your X, the input, multiply by your WXH. So X at the rate WXH. After this, your A1, or I should say Z1, right? Oh wait, Z1 is already done. Now to have the A1, I'll have sigmoid, and on top of that I'll be passing Z1. After this, to get Z2, I'll have the matrix multiplication of inputs from the hidden layer, that is the A1 values, and matrix multiplication with WHY. And after this, we are having Y hat, or A2, again, whatever you'd like to call. The reason I'm calling it Y hat is because I just saw that over here also we have written Y hat. So I'll just go with Y hat, and my Y hat will be equal to sigmoid of Z2. Simple. And if I want to talk about the in terms of comments, what are the shapes of everything? So the output of Z1 will be what? See, X was 4 cross 2, right? 4 rows, 2 columns, and then the WXH was 2 cross 4. So the output of this will be a 4 cross 4 matrix, just like this for A1. Because I'm not really doing any kind of changes over here, so it's still going to be 4 cross 4. But for the Z2, A1 is in the shape of 4 cross 4. And then the WHY is in the shape of 4 cross 1. So the output of this is going to be 4 cross 1. Then Y hat, there is no difference over here. No changes in the formula, it's just a transformation basically. So 4 cross 1 will also be the output for this. So we are done with our forward propagation equations as well. Now after this, we are having the backward propagation, where we had prepared our D1, D2, and along with that we were also having the DJ, DWXH and DJ, DWHY. First of all, let me prepare our delta 2. So what was the delta 2, if I help you remember? I go on the top. In this formula, the delta 2 is actually the error term multiplied with the sigmoid derivative of Z2. So this is your delta 2 term, D2. It's present in both the equations. So let's first create that. And the way that we had created this was with the help of element-wise multiplication. So keeping that in mind, let's try to have our delta 2. So it's the error term, which is my Y hat minus Y, element-wise multiplication with what? With the sigmoid derivative, the function that we had created over here, sigmoid derivative, this is what I'm calling, on Z2. So my delta 2 is ready. What were the shapes over here? We know that Y and Y hat both are 4 cross 1. So even if you perform the subtraction, the shape over here will be 4 cross 1. And then for the sigmoid derivative of Z2, because Z2 is in the form of 4 cross 1, even that is 4 cross 1. And therefore the output over here, because we are performing the element-wise multiplication, will also be same, that is 4 cross 1. So we are done with the delta 2 part. Now after the delta 2, I can simply compute my DJ, DW, HY. So that is going to be equal to D2 multiplied with A1. So if I scroll down. So DJ, DW, HY will be equal to my delta 2 and A1. If I talk about the shapes over here very quickly, the delta 2 is having a shape of 4 cross 1 and A1 is having a shape of 4 cross 4. So now what do I want? I want my DJ, DW, HY to be of the shape of let me see over here, WHY is of shape 4 cross 1, so this should also be 4 cross 1. So how can we do this multiplication so that the output is 4 cross 1? That's what I need to think. So over here I can have matrix multiplication of my A1 with my delta 2. So over here I can say that A1 matrix multiplication with delta 2. And that's what exactly I'm going to write over here, that my 4 cross 1 is going to be the output. If I have my 4 cross 4 matrix multiplied with 4 cross 1. Great. So we are done with DJ, DHY. Now we are left with DJ, DWXH. So for that, I first need to compute my delta 1. So now what will be my delta 1 is what we are going to think about over here. So delta 1 is first of all delta 2, and then it was matrix multiplication with WHY transpose. Okay, we had done the transpose of this to make sure that the output of this shape will be 2 cross 4. So there was a matrix multiplication in between with the transpose of WHY with the delta 2. That was my delta 1. After having the delta 1, I was going to multiply that with sigmoid derivative with the help of element wise multiplication. After that, I'll be simply taking the transpose of X and do the matrix multiplication with that delta 1 to get my final output. And therefore, if I just scroll down, and over here I'll prepare my delta 1. So delta 1 is going to be my delta 2, and the delta 2 is going to be having the matrix multiplication with WHY transpose, and the output of this, okay guys, the output of this is simply going to be multiplied with sigmoid derivative. I believe Z1, I'll just cross check it once. Yeah, Z1 over here. And therefore, the shapes over here would be, for delta 2, I know that the delta is going to have 4 cross 1 shape. So 4 cross 1, that's going to be matrix multiplication with what? WHY, transpose of that. WHY is 4 cross 1, so the transpose of that will be 1 cross 4. So the output of this is going to become 4 cross 4. So that 4 cross 4, if I do the multiplication of sigmoid derivative of Z1, which is going to be a 4 cross 4, output of this will be 4 cross 4. And then finally we are having the DJ, DW, XH. And for this, it will be delta 1, which is of the shape 4 cross 4, which is going to be multiplied with X. But how? It's going to become X transpose multiplication of, or I should say matrix multiplication of delta 1. So X dot T, matrix multiplication of delta 1. And therefore, if I talk about the shape of this, so X transpose, X was 4 cross 2, so XT will be 2 cross 4. And then delta 1 is 4 cross 4. And because we are performing the matrix multiplication, the output will be 2 cross 4. That's what we are looking forward to. So yes, everything makes sense now. And we are done with our final equations of the back propagations as well. Now after this, we are going to define our cost function, which is nothing but what? The mean squared error, RETURN. So mean squared of what? Y hat minus y. Run this code. Yes, we are having our mean squared error ready for us. Now after this, we are going to define our hyperparameters, that are the alpha and the epoch. So alpha, I'm going to set it as, let's say for example 0.08 maybe, and the epochs let's say 20,000. Now see, all of this kind of numbers I've already tested, and that's why I'm having it over here. But yeah, I've done this hyperparameter tuning. I've gone through changing multiple values of alpha, multiple values of epoch, and then I'm coming up with these values. But yeah, you can literally keep any values for the alpha in between 0 to 1, let's say 0.001 or maybe 0.01, whatever is your starting point, and then you try to tune it up by changing its values. And also the epochs, you can start with 100, and then if you think that your cost is still decreasing after 100 epoch, there is no stabilization, or I should say the convergence, which is able to be seen over there, you can go with more epochs. And that's why 20,000 epochs is what I am able to reach with. And over here, after doing all of these things, we are about to start with the training part. Now, if we had completed our module on the machine learning, where we had coded over there from scratch, then understanding this will be a piece of cake for you. The first thing that we have done is the empty list that I've created for storing all the cost during the training process. And then for the training part, I am having I in the range of total epochs. Unlike what we did in the machine learning with linear regression, where we had while loop, that I was looking into the convergence part to break the loop. Over here, I'm going to run it for 20,000 epochs. Now, if you want, you can have some kind of if statement over here. and also check for that condition. If the cost values are converging, then you can also terminate the loop even if the epochs are not yet completed. So over here, that kind of code you can surely go ahead and try it by yourself. But yeah, for now I'm just going to try for 20,000 epochs. And the first thing would be to get my forward propagation. What kind of inputs it takes? Let me press comma and see X, WXH and WHY. So in place of X, I'm having capital X, and WXH and WHY is as it is. And in the backward propagation, what do we have? Let's see. It is Y hat, Z1, A1, Z2. So all of these things we're getting over here will be passed as an input to this backward propagation. Now after this, we are going to implement our gradient descent over here and call this as what? Update weights for gradient with the help of gradient descent. So WXH, the whatever is the current value, I'll do the subtraction with alpha times the DJ DWXH that I'm getting output from the backward propagation. And the same thing for the WHY part as well. Copy this, paste it over here. I need to have a negative sign to show that it's WHY is equal to WHY minus alpha of this. I just need to change this WXH to WHY. And after this, I'm going to compute the cost. After the cost is computed, I'll append it in the empty list. And then I'll be printing my history after every 1,000 epochs, not 10,000, 1,000 epochs. So I'm going to run this code cell. Okay, there is an error over here. The error is that epochs are not defined. Maybe I did not run the code cell. Yeah. Now if I run this code, yes, we can see that after every 1,000 iterations, the cost has been displaying. And you can see that the cost is continuously decreasing. And over here, it's still decreasing, to be honest. But yeah, over here 20,000, even if the cost is this value, it's really good. And these are our final WXH and WHY that got updated. So that's what I'm getting over here. This is my WXH. Initially it was 0 point something everywhere, but now you can see that there are some negative values, positive values mixtures. And for the WHY also, the values were completely in between 0 to 1. But now you can see multiple different values which the model has given to us. And then now they are saying us that, you know what, now you can go ahead and check this particular thing if it's working fine or not on any kind of test data set. Over here, however, we are not having the test data set because we have assumed the whole data set to go over here as a part of the input. But yeah, let's see that for the training part, how it's really working. All right. But yeah, for the testing part, if you're having some kind of data, you can pass that in. But yeah, it was just for the understanding purpose that how it's really going to work. And you can see that it's very much similar to what we had implemented in our linear regression. The only one thing they're saying is the sigmoid activation and multiple layers in between. So if you want to change this to, let's say, ReLU, you just need to compute a function for ReLU and implement that. And yeah, just don't forget, you will also need to have the derivative of ReLU, so on and so forth. Whatever kind of activation you are using, just make sure you are having its respective derivative function ready as well, because that's what we'll be using in the backward propagation. All right. So yeah, if you are using Z1s with the sigmoid over, with the ReLU, then over here you will be requiring ReLU derivative. So yes, that's about it. But if I go down now and look forward for the cost function, the graph of the cost function versus epochs, let's see how it's really going to look like. So plt.show, or what am I, yeah, plt.plot is what I'm going to do in between the cost output and the epochs. So I don't really need to type epochs over here, but yeah, I can do it if I want. But even if I do this, it's still going to give me a nice curve. So initially it dipped a bit and then it increased the cost, but then after that it's continuously decreasing. And that's what we are looking forward to. So as the cost is decreasing, we assume, and this kind of nature is, it might be because we are using the mean squared error over here instead of using, let's say, a binary cross entropy. So it might be because of that. But still you can see that after a lot of iterations, 20,000 iterations, it is able to converge. If you are using a binary cross entropy, it will be converging very earlier itself. But yeah, that's what we are saying, that if you're having cost function versus epochs, that's how the graph is going to look like. You can surely go ahead and customize this the way you want, but that's the output that we have achieved. And now we are going to test the model. I have created a function called as predict, where I'm passing the x1 value and x2 value by the user, and the final WXH and WHY values that our model has given us as a part of the output. And then I'm raising this kind of an exception that if someone passes the input apart from 0 or 1, then just tell them that make sure that the x1 and x2 can take any inputs. X1 and x2 cannot take any inputs other than 0 and 1. You need to provide x1 and x2 as either of them, 0 or 1. And what did you provide us? You provide us x1 with this value and x2 with this value. So really good way of displaying what kind of problem has been occurring to the user of this particular function. And after that, I'm just creating this array where I'm passing this x1 and x2 data from the user and then implementing the forward propagation, passing my x test data and wxh and why to get the y prediction. After that, I can set the threshold value according to me. 0.5 is what I have chosen over here by default. And yeah, if the y prediction is greater than 0.5, 1 is going to work or else 0 is going to work. So that's a prediction function. And then if I run this code cell, over here what I have done is, I have created this kind of a basic intro message that welcome to a basic ANN predictor. Choose either 0 or 1 for x1 and x2. What happens if I choose something else, 0.5? It's going to raise an exception that, okay, yeah, over here the exception error is not really raised. Something else is raised because of 0.5, the decimals that I've given over here. Because you can see that over here I've used integer. So I cannot give 0.5. Let me just give 2 for example. And then over here also 2. You can see that the exception has been raised that make sure x1 and x2 cannot take any inputs other than 0 and 1. You have provided x1 as 2 and x2 as 2. So now user knows that, okay, yeah, I just need to give exactly 0 or 1 in both the cases. So let me give x1 as 0, x2 as 1. And now the model is predicting the output as 1, which is indeed correct. When the two inputs are different, it should give you 1. Now what really happens if I give both the things as 1 and 1? The output is 0. Again, how we assume it to work. Remember guys, this is just for the training data. So training is done very well. That's what it is indicating. Even though we have not used bias, we did not use binary cross entropy. Still, it's working guys. Alright. So yes guys, the way that I've prepared this is by following a very simple Python. I'm asking users to give some kind of inputs. That I'm using the predict function that I've created over here, passing the respective inputs, and whatever outputs I'm getting, I'm just simply customizing it. That's it. So yes guys, that was about the complete code about how we have created this artificial neural network from scratch. Just make sure guys, over here in the upcoming modules, you will be creating the artificial neural network with the help of TensorFlow and Keras. Okay. And beyond this program, if you're working on some kind of projects, you might use a framework called as PyTorch. But yeah, for this program, we are just going to focus on TensorFlow and Keras till the last module itself. So yes, that's something that you should know about. And over here, the dataset we have used is pretty small, and hence we have exhausted all the possibilities in the training, and therefore the output is always accurate over here. But yeah, the reason it is always accurate is also because the training is done very well. Okay, if the training was not done in a really well manner, even this would not perform well. But over here, you have however understood that how to prepare a neural network from scratch if you have to. Just like this, if you want to add more layers, you will have more equations over here. If you want to use some different activation functions, you need to prepare its respective derivative function also, and then prepare your backward propagation equations respectively. And yes, boy, we are done finally with this complete code of the ANN from scratch. First of all, please pat yourself, because this is something that is a great achievement for yourself. Because trust me guys, a lot of people who are in the field of deep learning don't really know how the things are exactly working in the backend. So over here, once again, congratulations guys for completing this particular module. And I hope you were able to understand and have a lot of fun creating this ANN from scratch. At the same time, you understood that how exactly ANN works.